Welcome. Here we're going to be talking about rope problems in terms of calculating work. So they all have a similar kind of vein. We're staying at the top of a building or a cliff or whatever, and we're pulling a rope up towards us. So let's talk about work. In the context of rope problems, we're looking at a variable force. So this matters because it's the thing that means we have to integrate. The variable force, it's because the weight of the rope, which is the force, its downward force as its weight, is not constant. When I have 100 feet of rope, it's heavier. When I've pulled up and I only have 50 feet of rope left, it's lighter. So the weight of the rope, the force exerted on my arm, if I'm holding the rope, is variable. So work is going to be equal to the integral from our limits of integration a to b, of some force function f of x dx. So f of x is the force function. So let's go ahead and start. We'll begin with a pretty standard rope problem. We'll do it 3 different ways to represent the 3 main options for the placement of the origin. And then we will look at some more challenging kind of advanced problems. So the first example I'd like to do is I have a 100-meter building, a 80-meter rope hanging from the top of my building, and the rope has a density of 2.5 kilograms per meter. Now note that these are kilograms. Those are units of mass, not units of weight or force. So we'll need to do some more work there. So I have here my building. I've got my rope, which hangs down 80 meters. And then the height of my building is 100. I'm sorry, this drawing is not exactly to scale, but bear with me. So I have this is my scenario. We are going to calculate the work to lift the whole rope. Up the building and kind of coil it along, I guess, at the top of the building. So we have 3 options for where to place our origin. I'm going to do this problem 3 different ways for all 3 options. So I can place the origin at the bottom of the building. So this will be scenario A. My origin is at the bottom of the building. So for all of my options, I need to do a 4-step process. The first step is going to be to write a length function. So this length function describes the distance but the distance to my target. And the target is always going to be the top of the building because that's where I am. That's where I'm lifting my rope to. So when I begin with the origin at the bottom, I need to write this function, L of x. When x equals 0, here at the bottom, I am 100 meters from my target, which is the top of the building. When x equals 10, a little bit further up, I am 90 meters from my target, from the top of the building. So as I move up along my values here, the distance to the target gets smaller. So when x gets bigger, the distance gets smaller. That should indicate to you that there's some kind of subtraction going on. So when the origin is at the base of the building, the length function is always going to be the height of the building minus x. That will always be the length function when your origin is at the base of the building. The second thing I need to do is write a mass function. So the mass function, the mass of the rope is variable. I guess the mass that's still hanging is variable. As I pull the rope up, I have less and less mass that is below, that is still hanging down. So the mass function is always equal to the density of the rope or chain or whatever it is, times the length function. So in this instance, that's going to be 2.5 times L of x, which is 100, minus x. The third thing I need to do is write a force function. So this is really, my goal is to have an integral, but I need a force function to put inside my integral. So I need to write my force function. I have an equation for mass, which is in kilograms, because my density was kilograms per meter, and I multiplied it by length in meters. So in order to write my force function, I need to multiply force is mass times acceleration. The mass is here, acceleration for the purpose of problems that happen on planet Earth will be gravity. So it's I'll use 9.8. You can use more decimals if your class requires it. But 9.8 times my mass function, which is 2.5 times 100 minus x. So that is my force function. The fourth thing I need to do is integrate to find work. So work is equal to the integral of my force function, which is 9.8 times 2.5 times 100 minus x. I need to determine my limits of integration. So always think of when I start pulling on the rope. So my origin is at the base of the building. So that's my position of reference. I'm standing at the base of the building and I'm looking up and someone's pulling the rope up. When they begin pulling the rope up, how far is the end of the rope from me? Well, it should be 20 meters away because it's an 80-foot rope. So my lower limit here will be 20. When they finish, well, the rope is all gone. So that will be all the way to the top of the building, which is going to be 100. So that's how you determine what the limits of integration are for this first scenario. If I plug that all into, if I evaluate that integral, I end up with 78,400 joules. So that is scenario 1, or scenario A, where the origin is at the base of the building. Let's look at our next scenario. So I have the same situation. I have my cliff or my building. I've got my rope. And I've got the height of my building is 100. Okay, so the next scenario, scenario B, is that I can place my origin at the base of the rope. So for scenario B, that's where my origin lies. I'm going to do the same exact series of steps that I did in the first scenario. I'm going to write a length function. Again, I'm looking for what is the distance between my point of reference and the target, which is the roof of the building, the top of the building. So when x equals 0, I am 80 meters from the roof of the building. When x equals 10, I am 70 meters from the roof of the building. So that should indicate to you, again, the further I go up in x value, the smaller my distance to the target gets. So that should indicate to you that there is subtraction occurring. So it will be the length of the rope minus x when you place your origin at the base of the rope. The second thing I need to do is write my mass function. So mass function is always going to be the density, which was 2.5 times 80 minus x. The third thing I need to do is write my force function. This is the same, except I just carry my L of x through. So these three steps or steps 2 and 3 are exactly the same, except you just carry that length function through. So instead I'll have 9.8 times 2.5 times 80 minus x. And then the fourth step is going to be to integrate to find my total work. So when I integrate, my function here, I do need to, again, pick my limits of integration. So once again, if my point of reference is at the base of the rope, let's say there's this, kind of hovering platform standing there. So I'm standing at the base of the rope. When the person at the top of the building starts to pull the rope, when they first start to pull the rope, the distance from my location, which is this kind of floating platform, to the end of the rope is 0. I am exactly at the end of the rope. As it moves away from me, they are going to carry it all the way to the top of the building. And when it's all gone, the end of the rope will be 80 meters away at the top of the building. So that's how you determine the limits of integration. And when I plug this function in and evaluate it, I get exactly the same answer. So that's the key with all of these problems, is that there's 3 different scenarios, but they all get you exactly the same answer. So that's scenario B, and it gets me the same number, the same value for work, which is 78,400 joules. Let's now look at our third scenario. So scenario C, I think we can fit it on the same page here. So let me just put it over here. So scenario C is that you put the origin at the top of the building. So when you do scenario C, there's one change, which is that the positive x-axis is going to be down towards the end of the rope. So be aware of that. Positive x is toward the end of the rope. I'm going to go through my exact same process. The first thing I'm going to do is write my length function. Now, if I'm starting at the top of the rope, remember that the length is the distance from your current position of interest to the target, which is the top of the building. So if my beginning point of reference at the origin, when x equals 0, is at the top of the roof, the distance from me to the target is 0 because I'm already there. As x moves down, as we increase x, say x equals 10, then the distance is 10. It's the distance from the target. So as you go down, you're literally just looking at how far along the rope are you. That is the distance to the target. So when the origin is at the roof, the length function is just x. There's nothing else. Then again, the second and third steps are the same, except we carry that length function through. So the mass function is going to be 2.5x. The force function is going to be 9.8 times 2.5x. And then the fourth step is going to be that integration. So I need to integrate. I'm going to look at my limits of integration in just a second. I have my force function here. 9.8 times 2.5x. Excuse me. And then I need to determine the limits of integration. So in this instance, because I'm pulling the entire rope up, I will just say, well, I go from 0 to 80. The rope is 80 feet long. So there's no really kind of trickiness to that when you're doing the entire rope. There is a little bit of trickiness to it when you're doing a portion of the rope, which we're going to talk about next. But that is the basic scenario for a rope building or a rope problem. You have a rope, you know the density, you are pulling it all the way. Now let's look at some more advanced type problems that add different contingencies to this. So the first one is going to be what I like to call a partial pull. So let's say what we want to calculate the work to pull up half the rope. So in this scenario, we're looking at the exact same situation. I still have my building. I still have my rope, which is 80 meters. And my building is still 100 meters tall. But instead of pulling the rope all the way to the top, I'm just going to pull it half the way. So when you're doing these problems, the fact that you're only pulling half the rope up will not change steps 1, 2, and 3. So your force function is going to be exactly the same as it was in the scenario where I'm pulling the full rope up. The only thing that changes is the fourth step, which is our work step, and it changes the limits of integration. So for scenario A, that was the origin at the base of the building. And you can look back in the video if you like. The force function for that was 9.8 times 2.5 times 100 minus x. So that was my force function when the origin was at the base of the building. In order to pull up only half of the work, I need to adjust the limits of integration on my work equation. So I'm going to copy this, my work integral. I'm going to copy this force function exactly. That is exactly what I had in the previous problem. I need to adjust the limits of integration. So the question that I ask myself is, how far from my location, from the origin, which is my point of reference, is the end of the rope? So at the beginning, when they first start pulling the rope, the distance from my location to the end of the rope will be 20 meters. So I'll start with 20. When they finish pulling half, so the rope is 80 meters, and that means they're going to be pulling 40 meters of rope. When they finish the pull, how far is the end of the rope from the origin, from my point of reference? Well, it's 40 meters higher, so it's going to be 60. So those are the limits of integration when the origin is at the base of the building. Scenario B, the origin was at the base of the rope. The force function was 9.8 times 2.5 times 80 minus x. That function is not going to change. The work, again, is going to be the integral, and I need to decide on my limits of integration. So my limits of integration, now I'm standing at the base of the rope. So when they first start pulling, the end of the rope, how far am I from the end of the rope? Well, it's 0. It's right where I am. They're going to pull it up 40 meters, and so at the end of the pull, it will be 40 meters away from me. So it will be 0 to 40. Those two are pretty straightforward. Scenario C is the one that does get a little tricky. So this is the origin at the top of the building. So here I need to again, I apologize. The force function in this scenario was 9.8 times 2.5x. So I have my integral, and I need to determine the limits of integration for this integral. So this one, when you're at the top of the building, when they start pulling, the end of the rope is 80 meters away. When they finish, and again, they're only pulling half of the rope up, so they're only doing 40 meters worth, it is the end of the rope is 40 meters away. So when we do work, we always put the smaller of the two values as our lower limit. So don't let this confuse you, the fact that at the beginning it's 80 meters away and at the end it's 40 meters away. We always still put the smaller value as the lower limit and the larger value as the upper limit. So when I plug these, all three of these equations in and evaluate them, I get the exact same answer for all three, which is 58,800 joules. So that is what you do if you're pulling up just a portion of the rope. The next kind of advanced scenario we can encounter is, what if there is a weight at the end of, or a mass at the end of the rope? So in this instance, I have still, let's begin, I have my same scenario. I've got an 80-meter rope and a 100-meter building. But in this instance, at the bottom of the rope, let's say I have a 20-kilogram mass. So there's an object at the end of the rope. Various word problems will put various objects there. It might be, I don't know, it might be a piece of construction equipment. It could be a live animal. Who knows? But the point is that it's a mass that does not change. So this matters. The mass of the rope changes. As I pull up the rope, I have less and less rope dangling. So that's a variable mass. But the object, whatever it happens to be, livestock or what have you, at the end of my rope, that is going to have a constant mass. It's not going to change. So when I do these problems, the only thing that changes is the mass function. And we add the mass at the end as a constant. So we add the constant mass at the end. So let's do this for scenario A. Remember that our length function for scenario A, this is unchanged, was 100 minus x. So scenario A was when I had my origin at the base of the building. So I had my length function was 100 minus x. My mass function, this is what's going to change. So the density of my rope remains unchanged. I'm still going to have the 2.5 times 100 minus x. At the end of the function, I simply add the mass, that is whatever the kilograms happens to be. Here it's 20, but it could be 50 or 100 or whatever. Whatever that mass is, you add it here in the mass step because it's given to you as a kilogram. Kilograms are mass, not weight. The third step then, I'm going to carry that mass function forward into my force function. So do be careful of your parentheses. It needs to be 9.8 times the entire mass function. So make sure that plus 20 is still in there, that it's that whole thing. And then the fourth step is going to be to integrate. I have my force function here, and I just need to determine my limits of integration. So if this were, I don't know, a small child or something that we wanted to rescue, we would pull it the whole way up. We would go from, 20, because that's how far the rope is when we begin, to 100, which is how far the rope is when we're done. That's the top of the building. And we would have this entire thing, 9.8 times 2.5 times 100 minus x plus 20. That whole thing is what would be evaluated. I encourage you to either use technology to integrate that, or you can simplify it algebraically. You certainly don't want to leave it this way. You'd want to probably simplify it before you actually evaluated it. But the answer for this one will be 94,080 joules. So that's what happens if we have a mass at the end of the rope. There is kind of one more thing that we can be asked to do, which is we can be asked to determine how far an object is moved. So let's go ahead and do an example like that. So this is kind of a combination because it's going to be a partial pull. It's also going to have a mass on the end, but we have this additional complication where we're given work in joules. And we have to find the distance. So this adds a little bit of a complication. Generally speaking, if you're working on a problem and they give you work, you know that you're going to end up solving for one of the limits of integration. So be kind of attuned to that in problems. If you have joules, that means you're being asked to find something else, usually length or distance. So let's consider another problem. Let's say I have a 200-meter rope, and at the base of that rope, I have a 50-kilogram mass, and I am told that 250,000 joules are applied to this scenario, to lifting the object. And the question is, how far will we move it? So in this instance, we're going to go ahead and start the problem up the same way because we still need a force function to put into our integral. So let's begin that way. The first thing we'll do is set up our length function. I chose to set this up having the length at the base of the integral because I like to do it that way, partly because, the base of the object here, partly because then when you do the lift, it will make sense in terms of the distance traveled. So when you find the distance, you won't have to do any additional work on the back end. And we can talk about what that means in a second. But first, I'm going to do this problem. So I have my length and my origin is at the base. So it will be the height, the full length of the rope, the height to my distance to my target, minus x. The second thing I'm going to do is write my mass function. And I do have mass in this problem. I apologize that I didn't give that to you. The density of the rope was 0.5 kilograms per meter. So the mass function is going to be 0.5. Oh, I apologize. I can't read my own writing. 1.5. Sorry about that. So of 1.5, which is my mass, times 200 minus x, that accounts for the mass of the rope. I need to account for the mass of my object, which is just 50 as a constant at the end. So if I distribute this all out and add the 50 in, I end up with 350 minus 1.5x. The third step is going to be to write the force function, which will always be gravity times your mass function. And when I multiply all of that out, I get 3,430 minus 14.7x. So this is what needs to go into my integral. That's my force function. So the fourth step is to write my integral. So work equals the integral of my force function, which is 3430 minus 14.7x dx. I need to determine the limits of integration, but I don't know. So I have been asked to find how far will we move it. that tells you that you're being asked to find one of the two limits of integration. So I know that if my origin is at the base, I have to start my pull at 0. I have no other options. That's where they start, right? The object is resting on the ground and it starts to be pulled upwards. And that is where my point of reference is there on the ground next to the object. So I know that I'm starting there, but this how far will we move it, that is an unknown. I'm going to use B just as a variable. You could use any letter you want. I usually don't use X just because X's appear elsewhere in my problem. I don't want to get confused. But that is what we're going to be doing. We're integrating from 0 to B. I know how much work was applied. So I applied 250,000 joules, and that is equal to this integral from 0 to B of 3430 minus 14.7 x dx. So at this point then, I need to take this antiderivative. So when I take the antiderivative, I'm going to end up with 3430x minus 14.7 over 2x squared. That is going to be evaluated from 0 to 2. Oh, sorry, not 2, I apologize. 0 to B. I'm not going to worry about the fact that B is a variable. I'm going to treat it like a number and plug it in the same way. So this is going to be equal to 3430B minus 14.7 divided by 2 is 7.35. So 7.35b squared. That's my first component. And then when I plug in 0 for x, I just get 0. So that's a straightforward part. So I still have this formula that 250,000 is equal to 3430b minus 7.35b squared. At this point, I now have a quadratic equation. So I can use the quadratic formula, but first I need to set everything equal to 0. So I will subtract the 250, and I'm going to rearrange these so that my square term is first. So I'll have negative 7.35b squared plus 3,430b minus 250,000. This I can then plug into the quadratic formula and solve for B. There will be two answers. The two answers are going to be B equals 90.4 meters and B equals 376.3 meters. So then we need to do a logic check because we cannot lift this longer, a further distance than our rope is. We started with a 200-meter rope, and so we have to pick the answer that makes sense. We can lift it 90 meters. We can't lift it that other one, but because of the nature of what quadratics look like, we need to pick the answer that actually makes sense. So at the beginning of this problem, I said that I was going to set the origin at the base, and I talked about how it's a little bit easier. And so here, if you're not clear, or if you have that question of what happens if you put the origin at the top of the rope, I'm going to do this exact same problem. I'm going to do it with the origin at the top of the rope. So let's go ahead and do that. So I have the same scenario where I've got my 200-meter rope. I've got my 50-kilogram mass, and I know that my work applied was the 250,000. And I'm looking to see how far I can move the rope. So if I put the origin at the top of the rope, it changes my functions a little bit, and it also changes my limits of integration. So my length function when my origin is at the top will just be x. My mass function is going to be 1.5. My rope density was 1.5 kilograms per meter, so it's 1.5x. And then, of course, I have my constant mass, my 50, at the end. My force function is going to be the 9.8 times my mass function, which is 1.5 plus 50. And when I multiply this out, I get 14.7x plus 490. Okay, so now I need to do my integration for work. Work is equal to the integral of force. So I have inside my integral the 14.7x plus 490. The question is, what do I do as my limits of integration? Remember that when we are pulling from the top, we pull kind of the last half of the rope. So I don't know where where the closer position was going to be. That's unknown. The question is, how far off the ground am I going to get it? And that closer position is unknown to me, but I know that I start at 200. So you have to have that little bit of a logic shift. And I see errors with these bounds sometimes when students put the origin at the top. So that's why I like to do it the way I did it previously, which is to put the origin at the bottom of the rope, even though it makes your equations a little bit messier. Okay, so now I do the antiderivative. I set it equal to 250,000. So I have 14.7x squared over 2 plus 490x, and this is going to be evaluated from A to 200. When I plug in my values, I get 14.7, times 200 squared over 2 plus 490 times 200 minus 14.7a squared over 2 plus 490 times a. So this is all still equal to 250,000. So when I do all the math there and I get everything, I'm not going to show it because I showed that in the previous part. But I'm going to simplify these so that I just have a quadratic. I'll subtract the 250 over to the right-hand side so I can set it equal to 0. And then I'll use the quadratic formula to find the solutions. I end up with two solutions for A. I get A is 109.6 meters, and I get A equals negative 176.3. So I'm going to eliminate the negative answer. I'm going to be looking here at this positive answer, 109.6. Here's the problem. This, when our origin is at the top of the rope, the positive axis is down towards the ground. So this is 109.6 meters. This is the distance from the origin, because that is our point of reference, right? So we have to be careful. In the previous solution, the 90.4 is also the distance from our origin, but the origin is at the ground. So that is the answer to how far above the ground I was able to lift the weight, the object. But in this instance, because this is a distance from my origin, if I want the distance from the ground, distance from the ground, I need to subtract from 200. So the total height is 200. The distance from the ground is going to be 200 minus the 109.6, which should be the same answer we got in the previous problem, which is the 90.4 meters. So be a little bit cautious when you're doing these problems, because the point of origin really does matter in terms of everything has to be consistent. If your origin is at the top, the answer you get is the distance from there. So it's all consistent throughout. And then if you need to determine what your question is asking you to answer. So that is what I had to say about work. Thank you for watching, and let me know in the comments if you have additional questions.